Section 6.2, Classification of the elements. Objectives are to explain why elements in the same group have similar properties, and identify the four blocks of the periodic table based upon their electron configuration. Some vocabulary to review will be valence electron. As you read in Chapter 5, electron configuration determines the chemical properties of an element. Writing out electron configurations using the Aufbau diagram can be tedious. Fortunately, you can determine an atom's electron configuration and its number of valence electrons from its position on the periodic table. The electron configurations for some of the group 1 elements will be listed in table 6.3. Right. So again, here's all group 1 elements, and notice how they end with S1, S1, S1. Right? It's just the principal number is what is changing here. All four configurations have a single electron in their outermost orbital. Recall that electrons in the highest principal energy level of an atom are called valence electrons. Each of the group 1 elements has one electron in its highest energy level. Thus, each element has one valence electron. The group 1 elements have similar chemical properties because they all have the same number of valence electrons. This is one of the most important relationships in chemistry. Atoms in the same group have similar chemical properties because they have the same number of valence electrons. Each group 1 element has a valence electron configuration of S1. Each group 2 element has a valence electron configuration of S2. Each column in groups 1, 2, and 13 to 18 on the periodic table has its own valence electron configuration. The energy level of an element's valence electrons indicates the period of the periodic table in which it is found. For example, lithium's valence electron is in the second energy level, and lithium is found in period 2. Now look at gallium with its electron configuration of argon 4s2 3d10 4p1. Gallium's valence electrons are in the fourth energy level, and gallium is found in the fourth period. Elements in group 1 have one valence electron. Group 2 elements have two valence electrons. Group 13 elements have 3 valence electrons. Group 14 elements have 4 valence electrons, and so on. The noble gases in group 18 have 8 valence electrons, with the exception of helium, which has only 2 valence electrons. In this figure above in 6.7, it shows how the electron dot structures that we learned in Chapter 5 illustrates the connection between the group number and the number of valence electrons. Notice that the number of valence electrons for the elements in group 13 to 18 is 10 less than their group number. Right, so again, kind of goes back to that trick I was teaching you. Everything in this group has one valence electron. Everything in group 2 has 2 valence electrons. Everything in group 3 has 3 valence electrons, right? 4, 5, 6, right? 7, 8 valence electrons, with the exception of helium. The periodic table has columns and rows of varying sizes. The reason behind the table's odd shape becomes clear if it's divided into sections or blocks representing the atom's energy sublevel being filled with valence electrons. Because there are 4 different energy sublevels, S, P, D, and F, the periodic table is divided into 4 distinct blocks as shown below. Right, you have your S block elements, your P block elements, your D block elements, and then below, right, you have your F block elements. And again, we'll sometimes refer to your transition metals as D block elements. You refer to your F block elements as your inner transition elements. Your S and P block elements will be referred to as your representative elements. And notice how in this periodic table we have that metalloid staircase that was spoken about in 6.1. The S block elements consist of groups 1 and 2, and the elements helium. Group 1 elements have partially filled s orbitals containing one valence electron and one electron configuration ending in s1. Group 2 elements have completely filled s orbitals containing two valence electrons and electron configurations ending in s2. Because s orbitals hold two electrons at most, the S block spans two groups. After the S sublevel is filled, the valence electrons next occupy the P sublevel. The P block, comprised of groups 13 through 18, contain elements with filled or partially filled P orbitals. There are no P block elements in period 1 because the P sublevel does not exist for the first principal energy level, or n equals 1. The first P block element is boron in the second period. The P block spans 6 groups because there are 3 P orbitals. It can hold a maximum of 6 electrons. The group 18 elements, also known as your noble gases, are unique members of the P block. Their atoms are so stable that they undergo virtually no chemical reaction. The electron configurations of the first 4 noble gas elements are shown below shown in table 6.4. Both the s and the p orbitals corresponding to the period's principal energy level are completely filled. This arrangement of electrons result in an unusually stable atomic structure. Together, the S and P blocks comprise what we call the representative elements. The D block contains the transition metals and is the largest of the blocks. Although there are a number of exceptions, D block elements are usually characterized by a filled outermost s orbital of an energy level n and filled or partially filled d orbitals of energy levels n-1. As you move across a period, electrons fill the d orbitals. For example, scandium, the first d block element, has an electron configuration of argon 4s2 3d1. Titanium, the next element on the table, has an electron configuration of argon 4s2 3d2. Note that the titanium's filled outermost s orbital has an energy level of 4, while the d orbital, which is partially filled, has an energy level of n equals 3. As you read in chapter 5, the Aufbau principle states that the 4s orbital has a lower energy level than the 3d orbital. Therefore, the 4s orbital is filled before the 3d orbital. The 5d orbitals can hold a maximum of 10 electrons. Thus, the D block spans 10 groups of the periodic table. The F block contains the inner transition metals. Its elements are characterized by a filled or partially filled outermost s orbital and filled or partially filled 4f and 5f orbitals. The electrons on the f suborbital do not fill their orbitals in a predictable manner. Because there are 7 f orbitals holding up to a maximum of 14 electrons, the F block spans 14 columns on the periodic table. Therefore, the S, P, D, and F blocks determine the shape of the periodic table. As you proceed down through the periods of the principal energy level increase, as do the number of orbitals containing electrons. Note that period 1 contains only S block elements. Periods 2 and 3 contain S and P block elements. Periods 4 and 5 contain S, P, and D block elements. And period 6 and 7 contain S, P, D, and F block elements. The development of the periodic table took many years and is still on an ongoing project as new elements are synthesized. Go ahead and look at an example, right? the electron configuration, and the periodic table. Strontium, which is used to produce red fireworks, has an electron configuration of krypton 5s2. Without using the periodic table, go ahead and determine the group, period, and block of strontium. All right, so far the only thing that we have is we know that the electron configuration of this is krypton 5s2. We know just by looking at this it's going to be the 5th principal energy level, so it must be in group period 5. And if we look at that superscript, it is S2, which tells us that it's going to go ahead and be in group 2. Right? And because it is an S, we know it is going to be in the S block of elements. Right? And because of that, we could also go ahead and take it one step farther, and we can go ahead and call it an alkaline earth metal. A summary section of 6.2. Summary of section 6.2. The periodic table has 4 blocks: S, P, D, and F. Elements within a group have similar chemical properties. The group number for elements in groups 1 and 2 equals the element's number of valence electrons, and the energy level of an atom's valence electrons equals its period number.